Well, thank you very much for this very kind introduction. I'm delighted to be here to visit this prestigious institution, and I hope that in the future maybe some closer interaction could develop. Who knows? So I decided to put together some material, information about melanin that sort of describes basic properties and other things. Of course, there will be a substantial component of our contribution to this as well. This is Krakow, actually the old castle, Wawel Castle, shown here. It's a very nice town, quite well preserved. It hasn't been destroyed during World War II, unlike the other cities, and we are very proud of it. Again, that's the cathedral on the Wawel Castle, and well, some of the parts of the old town. And this is called Collegium Maius. That's the oldest part of the university, Jagiellonian University. It was founded 1364, so it's rather old. And well, we had prominent students. One of the most prominent, Copernicus, in fact. He studied in this particular building, in fact.
So that's part of your campus?
No, it's the old campus. The new campus that we moved 10 years ago is actually outside the city. And all the sciences, natural sciences, will eventually get there. Already there is mathematics, biology, physics will move probably next year. So in the city, only the humanities will be left. Well, I'm sure that they are very... That's correct, yes. That's actually Collegium Maius, yes, the oldest university building. So that's a brief outline. Hopefully I will have time to touch on all those topics. So very briefly about biosynthesis, because I understand that melanin is not necessarily the best known material, biological material, and some physical-chemical properties, biological functions of melanin, skin and eye, role of oxidative stress in development of age-related macular degeneration. We are sort of interested in, well, at least one aspect of that disease, and changes of the retinal pigment epithelium melanin that is associated with age, and our model that we developed, how this in vitro photoaging of melanin modifies its property. So obviously melanin is a key component of the human pigmentary system. It is present mostly in the skin and hair, also in the eye. That's very important. Neuroepithelial cells and uveal tract. Well, but it's also present in the inner ear and in the brainstem, substantia nigra and locus coeruleus. And although people believe they understand why present in those locations, these, like the inner ear and brain, it's actually totally unknown. So it's pure speculation. So here is the, of course, picture showing the most obvious pigmentation of melanin, as you can see in the skin and hair. And there is a significant variation from this person that has very little melanin, Scandinavian probably, to this which has quite a lot of melanin. And of course, this person doesn't have any melanin at all because it's an albino. So there was a huge variation, but this is not a normal situation. It's actually pathology. Albinism is a form of pathology. So in the skin, hair, and eye, melanin is present in the form of discernible pigment granules. And this is atomic force microscopy, and this is electron microscopy of isolated retinal pigment epithelium melanosomes, you can see. Quite distinct shape, sort of ellipsoidal, maybe 2 microns in length, shorter than 1 micron in this direction. Well, that has, I think, important biological consequences. Melanin is synthesized by specialized cells called melanocytes, or those epithelial cells, and you can have two main types of melanin pigments, so-called eumelanin, which is brown-black, or pheomelanin, which is yellow-reddish. And then this pigment is synthesized in a series of redox reactions of dopa and cysteine dopa, respectively. Typically, both eumelanin and pheomelanin present to a various degree in the skin and hair. In the eye, it appears that eumelanin is the predominant pigment. Again, that's an interesting question. Why is that? So, just taking from hearing some basic steps, early steps of melanogenesis, you've got tyrosine and an enzyme like tyrosinase. Dopa is formed, hydroxylation, and then immediately oxidation to dopa-quinone, which is very unstable, very reactive chemically. And these pathways via dopachrome and DCA or DHI would lead to eumelanin. While if cysteine or glutathione is present at this stage, you will form, this cysteine would add to dopa-quinone, forming cysteinyl dopa, and then via, again, several steps, the key intermediate would be benzothioazine or some derivative of that. You will get pheomelanin. Obviously, in nature, there is almost impossible to get pure pheomelanin or eumelanin. Typically, you have a mixture of both. Now, people speculated for a number of years that melanin, it's a huge polymer. They call it actually oligopolymer, something which they thought might be a million Dalton or so molecular weight. But a newer sort of view is that maybe not so. Melanin may consist of relatively small oligomers, just several units. They would aggregate those units into the first level aggregation, in which the pi stacking plays a role. So these are very small now units, nano aggregates, if you wish. And then, of course, there will be another level of aggregation forming bigger aggregates, and finally larger, those pigment granules. But, of course, this model differs significantly from polymerization, because here, you have polymerization only very small units, and then you have some other type of interaction, not covalent interaction between those oligomers. And I think more and more data seem to support this model. There is key aspect of melanin properties, and that's disorder. I think that's important. And we are talking about chemical and physical disorder of melanin. And you can see disorder is at the stage of melanin precursors and melanin monomers. There are different melanin monomers. Unlike typical biological polymer, it contains different monomers. It's built of different monomers. Then there is degree of polymerization, oligomer size, and so on. So that is another disorder. Then positional isomerization, mode of coupling of monomer units. It's a coupling mode of disorder, and you can talk about the rotational disorder, electronic disorder, because there are different redox states of those monomer units, so-called functional units. And finally, aggregation interaction, which would give you supramolecular disorder. The disorder is important because in a model that would explain the absorption, optical absorption of melanin, disorder plays a significant role. There's another interesting property of melanin. That's the fact that melanin contains persistent free radicals. And you can divide them into two groups, intrinsic and extrinsic. The intrinsic, the free radical intermediates, they're probably trapped during different stages of melanogenesis. They are persistent, chemically rather non-reactive, and consists about 10 to 10% of all melanin radicals. And basically, you cannot get rid of them unless you simply chemically destroyed melanin. Of course, you can, with harsh treatment, harsh oxidative treatment, at high pH, you can obviously bleach melanin, and then it's destroyed. Then, of course, there are no more of those free radicals. But other than that, they are quite persistent. Now, they're extrinsic, perhaps more interesting, because they are determined by so-called comproportionation equilibria of the polymer functional groups. And they exhibit some reactivity. Concentration can vary within 1.5 order of magnitude. And comproportionation equilibrium is, that's what I mean. You have, well, those are just parts of those melanin monomers. But the key thing is that they're either fully oxidized, orthoquinones, for instance, orthohydroquinones, fully reduced. And they would exist in an equilibrium with orthosemiquinones. This would be for eumelanin. Now, if you have benzothioxide units, you will have slightly different sort of groups. Orthoaminoquinones or aminophenols, and they would be in equilibrium orthosemiquinone imines. Well, it may be just nothing of a big thing, but from a point of view of electron paramagnetic resonance spectroscopy, it's important because here you've got the unpaired electron, which is mostly localized on oxygen, which doesn't have magnetic nuclei, but here the electron is also localized on nitrogen, which does have magnetic nuclei. The spin is equal 1. And of course, these equilibria are governed and determined by different things. pH, the higher the pH, the more the equilibrium is shifted towards the semiquinone or semi-orthoquinone imine. Temperature and the presence of diamagnetic metal ions, because you can see that those groups can act as chelates, and they would form complexes with, say, zinc, for instance. So with plenty of zinc ions, you can shift the equilibrium towards the free radical form. Those guys, jabrils, yellow and black, and the hair of those jabrils would give, this is the black hair, and this is the yellow hair that contains pheomelanin, and that contains mostly eumelanin. And these are synthetic melanins, the cysteamyl dopa, which is a model of pheomelanin, and dopamelanin, which is a model of eumelanin. Well, the eumelanin signal is not very interesting. You can see it's just a single line, at least at X band, which is the normal, typical EPR spectroscopy. There are more sophisticated forms of spectroscopy these days. But the pheomelanin does contain a more complex signal. 1, 2, you can see here a little bit the third component. That's due to this hyperfine splitting on that nitrogen, which was in that unit I indicated to you. Well, using a W-band EPR spectroscopy, which is 10 times higher frequency, you've got some resolution now. That's the eumelanin in the presence of zinc. You see a distinct axial anisotropy, so we are getting some information. And for pheomelanin, you see also this axial anisotropy, but in addition, you see that beautiful hyperfine splitting now, 1, 2, 3 lines due to the localization of the unpaired electron on nitrogen. So, what are the biological functions of melanin that is present in the skin and eye? Well, basically, people believe that melanin acts as a natural sunscreen that protects pigmented tissues against adverse reactions could be induced by solar radiation. And there are some, epidemiological evidence that this might be true. So first of all, there is a distinct correlation between the resistance of human skin to UV-induced erythema and sunburn, something that probably it's quite typical in this geographical location if somebody is not wise enough to cover their skin. Constitutive pigmentation of the skin. Also, there is photoaging of the skin inversely correlates with its pigmentation. So the paler the skin, of course, it will faster photoage when there is no proper protection. There are epidemiological data suggesting that the incidence of solar radiation in related skin cancer is higher in individuals with genetically determined poor ability of the skin to tan and low pigmentation of the skin. And finally, melanin tends to protect the eye against several ocular diseases that can cause blindness. And these diseases include uveal malignant melanoma and age-related macular degeneration. And I will talk a little more about it later. Well, let's talk first about the physicochemical properties of melanin that might be relevant for its postulated photoprotective action. Well, there is just a short list of those, but I think quite important. Well, first of all, of course, melanin efficiently absorbed light, both UV and visible radiation, and converts energy of the absorbed photons into heat with high rate and yield. That's exactly what you expect from a good sunscreen. Molecules that are in the sunscreen formulation should absorb photons and with no chemical reaction. That should be just dissipation of the energy into heat, because that's the safe way of getting rid of the energy. Well, in addition, melanin quenches singlet oxygen and electronically excited states of certain photosensitizing molecules. I'll show you an example of that. Scavenges reactive free radicals, oxidizing and reducing. That's important because here the action might be more sophisticated than just acting as a sunscreen, obviously. And sequester redox active metal ions, which is also very important. There are problems if one wants to study some of the properties of melanin that I'm describing by standard physicochemical techniques. And that's because natural melanin is basically non-soluble in any of solvents we know. Of course, you can do some tricks. You can solubilize melanin by exposing to very alkaline media and then partially oxidize. But at the end, you get substantially modified, chemically modified pigment. So that's not exactly what you would like to do. People do it, but it's not necessarily the best way. So in our approach, we use synthetic soluble melanins. Again, this is not a perfect solution because the product is not obviously different from natural melanin. But some of the properties remain the same. So just a compromise. So we use laser flash photolysis to monitor interaction of melanin with excited states of other molecules. Time-resolved singlet oxygen phosphorescence to determine the efficiency of melanin to quench singlet oxygen. Pulse radiolysis to measure the ability of melanin to scavenge free radicals. And of course, EPR spectroscopy and some of the variety of those techniques to characterize melanin photoreactivity. Well, that's the optical absorption spectrum of soluble dopamelanin from 200 to over 1,000. As you can see that sort of shows, well, I mean, it's not an interesting spectrum, but it's a spectrum or the optical properties that you would expect from an efficient sunscreen. The efficiency increases with the energy of the photons, obviously. So it becomes much more efficient in getting, well, dealing with high energy photons. Broad monotonic absorption, almost monotonic, of eumelanin in both condensed phase and solution appears to be true electronic property of the constituent molecules. It's important because people speculated that perhaps this, what it's just shown, I shown a moment ago, it was due to light scatter and not absorption. But newer data seem to support that. And quantum chemical calculations proved that the absorption, emission, and excitation properties of eumelanin can be explained by simple heterogeneous mixture of oligomeric species. And there are several authors that contributed to that. Here are some data we obtained, well, quite a long time ago. But it's important. We observed here very efficient energy transfer between a molecule, which is, this is a derivative of a porphyrin, but it's a positively charged tetraanilinium porphyrin. and at neutral pH it's positively charged, and it would form complexes, ionic complexes with melanin, because melanin has, at neutral pH, negatively charged groups, so they simply interact by ionic interaction. And the consequences are quite dramatic. This is using a degenerated pump probe experiment exciting at 400 nanometers. You can see that, well, that's the, of course, absorption maximum of this porphyrin, or close to that. You see a very, fast bleaching because number of molecules have been transferred to the excited state. And then, of course, this bleaching lasts on this time scale forever. In fact, you can easily extend it to microseconds because, or nanoseconds, that's for sure, then microseconds, because singlet excited states in porphyrin, then via intersystem crossing, you get the triplet excited state, and the triplet excited state really long-lived, tens of microseconds, that's for sure. But if you have this interaction of melanin, so this complex is formed, you see now that this bleaching actually it sort of relaxes very fast. So, and this is due to very efficient energy transfer from the singlet excited state of the photosensitizing dye to melanin. Then, of course, the energy is dissipated into heat. So again, from the point of view of potential photoprotection, you've got an excellent mechanism and very efficient mechanism. Well, just a compilation of some of the work we did over years. Second-order rate constant interaction of dopamelanin with free radicals and singlet oxygen, which is obviously not a free radical. But what is important here, these are the redox potential, one electron reduction potential of those species. And, as expected, sort of, the higher the absolute value of that one electron reduction potential, the faster the bimolecular rate constant is of the interaction. I mean, that's something you would expect. Well, there are some interesting, perhaps, deviation from that. That has to do if the radical that interacts with melanin is either positively charged, which would stimulate such an interaction, also chemical interaction, or negatively charged, which would probably make this interaction more difficult. So let's talk about this, oxidative stress and AMD. Chronic oxidative stress in the outer retina is believed to play a role in the development of age-related macular degeneration, which is the leading cause of blindness in people over 60 in developed Western countries like United States. And that's basically what age-related macular degeneration is, or what patient with this would see. Now, this is a normal eye. This is an eye of a patient with AMD. As you can see that the central vision is blurred. So the patient would probably perceive light and some, contours. But of course, since the photoreceptor cells responsible for acute vision localized in the macular part of the retina, very small central part, and that is affected by this disease, that central vision is actually lost. What is interesting, people, that's a paper by Bock, people that work in this area tend to believe that the retinal pigment epithelium layer of the retina might be responsible for some of the key changes leading to this pathology. So the risk of oxidative stress in the retinal pigment epithelium, photoreceptor outer segments, is elevated by high oxygen tension, one of the highest actually, presence of endogenous photosensitizers, and peroxidizable substrates. And what's important, the role of melanin is unclear. And, well, our study, we want to at least try to understand some of the issues. So this is a section of the human eye. You see, we're talking about this part, the retina, and the retinal pigment epithelium is right there. Here it is. So that's a single cell layer. It is in an intimate contact with photoreceptor outer segments. And these are sort of shown melanosomes. They are there. That's why it's called retinal pigment epithelium. And well, there are certain things here. Light, of course, comes from here. And oxygen is supplied by the choroid, which is very well vascular system, and so keeps the outer retina at high oxygen concentration. It's important because metabolic rate of photoreceptor cells is very high, so you have to have enough oxygen to support this metabolism. So basic properties of retinal pigment epithelium: monolayer epithelium, apices opposed to photoreceptors, non-mitotic. So these cells do not divide. They stay for life, and if something goes wrong, obviously the other cells that were not affected critically would have to take the function of those cells that perish. And, of course, they contain melanin. RPE is essential for photoreceptor function and survival because responsible for trophic interactions, ion homeostasis, nutrient oxygen waste transport, and photoreceptor turnover. This is a critical thing because to keep the photoreceptor cells surviving, you have to have a very intense and regular turnover of photoreceptor outer segments. These are highly oxidizable parts of the cells. And if there is no turnover, the system would deteriorate. And in fact, there is a disease in the so-called the Royal College of Surgeons rats that they have genetic, because of genetic problems, their photoreceptor outer segment cannot undergo this turnover. There's biological renewal, so they born seemingly okay, retina okay, but within days or weeks they become blind because of that. So this is really critically important, this metabolic turnover. Well, eventually everything ages, and so is the retinal pigment epithelium, and you can see here that the flat mount of those cells actually, you can see very nice shape, the cells. But then it contains, this is a fluorescent material. It's called lipofuscin. And we have shown, and others as well, that it's photoreactive. It acts as an endogenous photosensitizer, generating singlet oxygen and free radicals. So if you accumulate too much of that, the consequences might be dire. Anyway, what we observed here is the age of human retinal pigment epithelium cells, of course postmortem, and as a function of age, and that's the rate of oxygen consumption. You can see rather significant increase over years. Many factors responsible for that. Among them, it's the accumulation of that lipofuscin, but there are some others.
You are looking at the basal surface or the apical surface?
This?
This is basal. Looks like a basal surface.
Well, it's a flat mount, you know. So you actually isolate.
This is an epithelial cell, right?
I'm sorry?
This is an epithelial cell, right?
Retinal pigment epithelium cells, right?
Yeah, they should have both surfaces, the apical and basal.
Yeah, but
from looking at basal surface, I assume.
Yeah,
this is a shape looks like a basal surface.
No, well, I'm not sure that I understand. I don't think that with mounting and using this microscopy, you would be able to distinguish the basal or the other.
Okay, let me ask you the question. Are these cells grown in a petri dish or
No. These cells have been isolated from human eye and then flat mounted, and then the picture is taken.
How do you make sure those, when you isolate it, you lose all the tight junctions and other things?
Well, of course.
Then how is this a true representation of what really happens?
No, I suppose it's my fault. I didn't make it clear. We are not trying to represent here any other aspect besides the fact that these cells accumulate lipofuscin, as you can see under, well, that's actually fluorescent microscopy, okay? That's the only thing we want to show in here, nothing else. Yes, please.
Where did you get eyeball cells from age 0 to 100?
Oh, good question. Unfortunately, this is not possible anymore. You know, in the 90s, we had access to, you know, there was such a thing as Wisconsin Lion Eye Bank. And I'm sure that there are such eye banks all over United States. But at that time, they were willing to, you know, make the material available to us, researchers, without any charge. There was no problem. We were able to get, and, you know, people donate, of course, tissue, different tissues, also eyes. And, of course, from the eye, you can use only cornea from transplantation. All the rest is, you know, left or thrown away or given to researchers. Well, it used to be, but now you have to probably pay several $100s for one eyeball. It's still possible, but very difficult to get and very expensive. So, you know, we were lucky that we were getting, you know, this over several years. In fact, this is not easy to accumulate that amount of material. Yes, of course. Yeah, sure.
So the
Yes.
increased rate of oxygen
Yes.
consumption
Yeah.
is not a metabolic consequence?
No, because this is a photoconsumption. Perhaps I didn't say that. Mostly lipofuscin. We have now information that lipofuscin is not the only contributor, but that's the main, no doubt. Yeah.
Is there an action spectrum?
Yes, we actually published such an action spectrum. Yeah, definitely. Right.
So blue light is sort of a peak.
Actually, even UV is more efficient, but from a biological point of view, you know, it's not important anyway, because the lens totally, actually, at least in adults, totally blocks light below 400 nanometers. So, yeah, the physical photochemical properties of lipofuscin are such that it would be, I mean, the efficiency to excite and generate those, you know, singlet oxygen and the radicals are higher at shorter wavelength, but photobiologically it's of no relevance. Right, so we also observed that, of course, melanosomes change their properties, appearance and everything, with age. And, well, this is just a picture showing, this is from a very young human eye, and this is for a much older human eye. You can see that the melanosomes become sort of heterogeneous. They change shape and some other things. Now, of course, that's fine. Morphology is okay, but we are more interested in other issues. Here is, we use the EPR spectroscopy to determine the melanin content in RPE cells from donors different age. And that's the power of EPR spectroscopy, because it you don't have to actually isolate anything. It's specific in cells. It will show you if such a cell, if cell contains melanin, it will show you mostly melanin, nothing else. So that's quite easy in a way. Of course, there is a huge individual scatter, and there are many data points here, as you can see. But the trend is rather obvious. With age, there is a significant reduction in the amount of melanin in retinal pigment epithelium. We got some newer data showing that even melanosomes, now isolated melanosomes from young, well, 20 to 30, or old, 60 to 90, would contain also different amount of melanin, normalized per granule. So that's we can now demonstrate that that's indeed there is a change in the content of melanin. Now the question is actually intriguing because, well, I will come back to this. what is the mechanism of how the system becomes, gets rid of melanin or changes the amount of melanin? It's not a trivial question because the metabolism of melanin is almost non-existing. I mean, there are no enzymes that would fully degrade at molecular level. And it appears that the RPE cells probably don't exocytose melanin outside. So there must be another process. And of course, we are proposing a specific mechanism that might be responsible for that in a moment. Anyway, there's also increased photochemical reactivity of that melanosomes from older donors because they faster photoconsume oxygen when irradiated with blue light and photogenerate superoxide anion. And the chloroform-soluble fraction of the granules photogenerates singlet oxygen. That's interesting. Well, this is just the basis of the spin trapping. As you can see, you use diamagnetic molecule called spin traps interacts with reactive radicals forming spin adduct, which is longer lived. Well, of course, its spectrum, EPR spectrum, should be informative to be able to identify the nature of that trapped radical. But its technique is well known and has been used for a number of years. Here's some data. You can see that that's oxygen consumption, irradiation with blue light. As you can see, that the slope becomes steeper for melanosomes obtained from older donors. And also the adduct, that's the adduct, that's the DMPO-OOH. So the superoxide anion is actually spin trapped, and then this adduct is hydrated. So you have the species. Those are the hyperfine splitting, so the simulation is quite good, showing that indeed we have superoxide anion trapped by this adduct. And again, the slope, the accumulation of that adduct with time during irradiation shows that the older melanosomes seem to be more photoreactive. Pretty much the same, but now we wanted to be more sort of specific. We were trying to isolate the soluble and insoluble fractional melanosomes when treated with chloroform methanol because such melanosomes with age could accumulate, excuse me, and not some other material, lipofuscin type. So we wanted to know if the residual, which is not soluble, would also show different photoreactivity. And indeed, this is the after forge extraction, the with age show higher reactivity. To some degree, also this superoxide anion. We wanted to determine whether there is singlet oxygen formation by this chloroform-soluble fraction of melanosomes. And we use this technique. It's well known. It's based on detection of specific products, oxidation product, cholesterol. You see that with singlet oxygen, cholesterol forms on these species, hydroperoxides, but 5-alpha, 6-alpha, 6-beta. But if oxidation is via free radical mechanism, it would form 7-alpha, 7-beta hydroperoxides. And these can be separated by HPLC and detected with high sensitivity by, electrochemical detector. Here is a polarographic detector, in fact, what we use. So, yes, indeed, these peaks are very specific for those products. As you can see, that for old and for young, well, this is 7, this is 5-alpha. We do observe significant formation of that singlet oxygen-specific oxidation product of cholesterol, showing that part of the material, which is in the older melanosomes, is also able to generate singlet oxygen. It's not melanin, obviously, because melanin does not have such properties. But the other part of material still can contribute to this oxidative stress in the system. So, enhanced phototoxicity. Yes?
That other material, is that within the lipofuscin granule?
No, that's actually part of the complex melanin granules. We isolate melanosomes from other granules, but by using differential ultracentrifugation in a sucrose gradient. So it's very sort of tedious procedure to try to separate different granules. And we think we are okay. This has been done twice, so it's mostly melanin because the density appears to be typical for melanosomes. But we cannot, of course, totally rule out that this melanosome is not modified by aging, which might end up and lead to this additional material which sticks or becomes part of the melanosome outer surface.
The melanin you talked about in the melanosomes in the old people versus younger people.
Right.
If you look at the composition of melanin, by which what I meant was whether it's an oligomeric state of the melanin. In the beginning of the talk, you mentioned there are various types of melanin present. Monomer, dimer,
Yes.
polymers, and so on. Is that composition of those polymer, monomer, etc. in the younger people versus the melanosomes that you isolate from the older people? Are they identical or are they different? Or is there any difference in the composition?
That's a very good question. And I can tell you that if we use our sort of standard procedure that it's been around for, I don't know, 20 or something years, it's developed by Japanese researchers, Ito in particular. They use chemical degradation of melanin, and then they characterize, again, species which are formed by this degradation. And based on that, they are able to distinguish between, say, pheomelanin, eumelanin, and maybe eumelanin, which is mostly from deca, carboxylic acid dihydroxyindole, or DHI. Well, based on such data, we were not able to see any significant differences between young and old. Now, the stacking other things, that may, of course, be modified, but we have no way of, approaching this in a sort of experimental way that we would be satisfied that this would lead to an unambiguous answer. So, exposure of RPE cells that contain older melanosomes or younger melanosomes to blue light results in abnormal cell morphology, substantial decrease in mitochondrial activity, loss of lysosomal pH, and cell death, particularly when the cells contain older melanosomes. Now, how this is done? Well, it's done by phagocytosis. So you actually expose cells in vitro to particles, and they're ingested, because RPE cells do phagocytose many different things. It's not specific to melanosomes by any chance, but they also do. And as you can see here, that the mitochondrial activity decreases when the cells that contain older melanosomes are irradiated blue light, while contain the younger melanosomes, or not irradiated, actually don't change too much. So one of the questions is, which is not trivial, is melanin photoprotective or it's phototoxic? And it's not trivial, because even though this is all true, which would contribute to photoprotection, also it's true that irradiation of melanin in the presence of oxygen leads to the formation of superoxide anion and hydrogen peroxide. So the question is, which process dominates? And we have some data. Well, first of all, we try to develop an in vitro model of aging melanosomes. And, we postulate that chronic photooxidation of RPE melanosomes induces critical modification of the physical properties, leading to reduced antioxidant capacity and enhanced photosynthetic ability. You have to remember that the red RPE cells are exposed to visible light, but for many years. So minute changes, and of course to oxygen, minute changes could accumulate over years and contribute to this change, reduction in the melanin content, and modification of the properties of melanin. So that's the idea. So we isolated porcine or bovine RP melanosomes, experimentally photobleached, well, partially photobleached, they are not really photobleached, with intense visible light to simulate aging. And of course, we had to use a huge intensity to simulate something that can occur over many years, as you can imagine. But anyway, with such thing, we were able to show that, yes, when not native or untreated melanosomes, for instance, inhibit peroxidation of lipids induced by iron ascorbate, the partially photobleached melanosomes actually not only that don't inhibit, but they actually stimulate this peroxidation of lipids. And this is shown by here rate of oxygen consumption or by accumulation of lipid hydroperoxides. And photobleaching also decreases the ability of melanosomes to inhibit iron-dependent generation of hydroxyl radicals and to sequester iron ions. Again, we use the spin trapping, typical Fenton system. So here is the hydroxyl radical adduct, and you can see that in the presence of native melanosomes, this was significantly inhibited, but photobleached melanosomes didn't make much change. Also, the amount of iron that is sequestered, and we tried two different approaches to determine the amount of iron, decreases with the degree of melanin photobleaching. Here, the degree is shown by number of hours that those melanosomes were irradiated with intense visible light. We also tried to use a more sophisticated approach, trying to determine the interaction of metal ions with melanin, and for this we used so-called saturation recovery EPR spectroscopy. Well, we took advantage of the fact that if you have fast relaxing metal ion, such as dysprosium, and it's a paramagnetic metal ion, and it is bound to melanin, due to dipole-dipole interaction, it would shorten the spin lattice relaxation time of the melanin radicals. And indeed, you can see that this is without metal ions, this is in the presence of metal ions, the relaxation time is shortened. And then, of course, some analysis of that process. But what we observed is that if the melanosomes not bleached, this is a concentration-dependent process, but for bleached melanosomes, the degree, the change, dynamics of that change is much more significant, suggesting that the approach, or the distance between the bound to melanin dysprosium ion and melanin-free radicals gets closer. And that's important because those radicals, as I mentioned, could contribute to photoreactivity by interacting with oxygen and some other species, suggesting that such melanin, partially photobleached or photoaged, if you wish, experimentally photoaged, might become more photoreactive because of some morphological changes of those granules. Here is an example to show you that the partially photobleached melanin also poorly protects or even stimulates lipid peroxidation, which is induced by blue light irradiation. And indeed, such photobleached melanosomes actually generate superoxide anion, or the adduct superoxide anion, DMPO. So here is the partially photobleached, here is the control unbleached melanosome, something in between, showing that the photochemical properties also change, again, consistent with what we observed for naturally aged melanosomes. So we can skip that. And, well, not much time, but I will try to be on time. So we used dynamic imaging-based cytotoxicity assay, individual RPE cells, and we try to determine whether there was any significant effect of melanosomes. The cytotoxicity was induced either by exposure of those cells to hydrogen peroxide, which is a known cytotoxic agent, or to blue light, so photic stress. And again, the melanosomes were fed into those cells by phagocytosis. Of course, to make this experiment meaningful, we would have to expose such cells to different particles, because phagocytosis by itself could have a significant effect on the cell's behavior. And indeed, that's what we observed. So, so here is, okay, you see those cells. You can see that blabbing of the cells when the cells are exposed to intense blue light. And that blabbing precedes propylium iodide staining of the cells. So it shows that we can monitor behavior or cytotoxicity in, well, real time on almost single cells. Here are some data we obtained, and you can see it's not a huge difference, but you can see that when cells contain black beads, polystyrene beads, or melanosomes, and the cells were exposed to hydrogen peroxide. I'm sorry, this is, these are melanosomes, and these are, of course, controlled black beads. You can see that there is some protective effect. It's not huge. Still, the net effect is rather convincing. Here's, again, shown for different concentration of hydrogen peroxide. These are control beads. These are melanosomes. So the effect of melanosomes, the protective effect of melanosomes seem to be apparent here. The photobleaching of melanosomes, so we could also introduce into the cells not only native melanosomes, but those photobleached melanosomes that model aged melanosomes in human RPE. Of course, these are bovine RPEs. They actually show that the blabbing is actually significantly increased when the cells are exposed to intense visible light. So photobleached melanosomes, if this is a good model for aged melanosomes, not only not protecting, but they actually stimulate this light-induced cytotoxicity. And this is a functional measure of local sublethal stress. It's granule movement. We were able to observe, well, to follow the movement of individual granules. You can see they move, that's a 5-second interval over 120 minutes. And what's important is that when, and of course those are trajectories that we can plot, that when cells are exposed to photic stress or to hydrogen peroxide, there is definitely a slowdown of that movement. Now we can monitor subthreshold doses of stress because the cells survive without any problems. But the organelle movements seem to be significantly slowed down. So it's a very good indication of sublethal effects. And well, you can see here that the phagocytous latex beads, when they are present, they are also slowed down, or endogenous pulsar melanosomes also slow down when irradiated with high enough doses of blue light. And this might be meaningful. You can see that, again, the effect depends on photobleaching. This is the degree of photobleaching expressed as hours of irradiation. As you see, the inhibition of such melanosomes increases, the inhibition of movement when irradiated with blue light increases with the degree of photobleaching. So such aged, experimentally photo-aged melanosomes become quite phototoxic. So, in summary, young, non-bleached melanosomes seem to protect RP cells against oxidative and photic stress. Even though for photic stress, the story is very complex because it would involve definitely screening effects, perhaps some antioxidant action of melanin, but the net effect depends on so many factors. It's sometimes very difficult to differentiate. You really must use control particles with similar optical properties to be sure that you actually control the experiment reasonably well. Photo-aged melanosomes become pro-oxidant and even phototoxic. The modified ability of partially photobleached melanosome to act as an antioxidant and photoprotective agent appears to be related to their reduced ability to bind and sequester metal ions and cationic photosensitizer, if they are used, of course, and their inefficiency to neutralize oxidative radicals and hydrogen peroxide. Although it's not clear whether similar light-induced oxidation bleaching of RP melanosomes occur in situ, because that's this is just a model. The consequences of chronic photo-induced changes in RP melanosomes may be a diminished capacity of melanin to help protect aged cells from oxidative damage. Structural changes of melanosomes induced by photobleaching can be monitored by high-frequency EPR and saturation recovery EPR using dysprosium as a unique molecular probe. Photobleaching of melanosomes induces a substantial modification in the topography of metal ion binding sites relative to melanin-free radical centers. These changes can increase the accessibility of bound to melanin redox active metal ions to reducing agents and molecular oxygen, leading to enhanced formation of reactive oxygen species, and may be responsible for the observed modification of antioxidant properties experimentally photo-aged bovine and porcine RP melanosomes. And finally, I'd like to acknowledge contribution of many people. First of all, my colleague Janice Berg from Medical College of Wisconsin. The significant part of the work was sponsored by a grant that we have from National Eye Institute. Mike Bolton, University of Florida. Jim Hyde from the National Biomedical ESR Center, Milwaukee. And these are my colleagues, my former PhD students. Now, Witek Korytowski is he's both in Medical College of Wisconsin and our university. Małgorzata Różanowska is at Cardiff University now. John Simon from Duke University, he uses the atomic force microscopy. And my former PhD students now are postdoctoral Grzegorz Szewczyk, Zaręba, and Żądło. And with this, thank you for your attention.